Up to this point in AP Physics 1, whenever I've asked you to graph one variable against another and then determine the explicit relationship between the two, it's been a relatively easy process because it's always been a nice clean linear relationship that we can easily find the slope of and the y-intercept and get a nice simple linear equation. But the thing is, though, is that there's a lot of things that are not linear or directly related. And how exactly can we go about analyzing those relationships, those nonlinear curve relationships, from a graph? And to be able to do that, we're going to utilize a data analysis technique called linearization. So think back to the very beginning of this year. One of the first things I asked you to do was to investigate the relationship between how high a ball was dropped and how high it bounced. And how exactly did you go about doing that? Well, you collected the data, you arranged it in a data table, then you plotted the height of the drop and the height of the bounce against each other, and lengthily it made that nice, clean, linear curve, real easy to analyze. But instead, let's imagine I'd asked you a different question in particular. Let's say we had this scenario here. We have a person standing on top of a building, and at time t equals 0, they're going to drop a ball, and we want to compare the relationship between how long the ball has dropped in seconds and how far it has dropped in meters. So it's time and its distance. And we know now, from all the kinematics and everything we've done to this point, that this is actually not a linear relationship. We could figure out a lot of the details just from physics alone, but let's say we didn't know any of that. This is the very beginning of the year. We have not really even touched physics yet. We've only been manipulating data so far. Well, if that's the case, how could we go about doing this? Well, when they find the data here, it should look something like this, where we have essentially the time, we're collecting it every second, between 1 and 5 seconds, and this is showing the distance the ball has dropped, and as you can see, the distance between every 2 points is increasing, because it is a non-linear relationship. So at 0 seconds it's at 0, 1 second it's at 5 meters, 2 seconds 20 meters, 3 seconds 45 meters, etc. And when we plot this, we get a nice, obvious curve. And you can probably recognize that this is a quadratic or parabolic shape, but let's not even really go that far with it yet, because really I just want to recognize I can't use everything we've been doing up to this point. Y equals mx plus b will not give me an accurate analysis of this relationship because it is not a linear graph. So what is linearization exactly? Well, it's essentially manipulating how we graph data so that the graph will, in essence, now be linear, or at least appear to be linear, in order so that we can analyze it in the way we usually analyze linear graphs, but then give us information about specific nonlinear relationships. And I want to be very, very clear here. I'm not asking you to change the data. You should never be changing the data you take from an experiment. So in that previous example, you got the times and the distances. Those remain the same. However, what we are going to change is we're going to change how the data is graphed so that we no longer have a curved line. We now have a nice, straight, linear line. Now, to be able to do this, we have to be able to recognize a few different graph shapes, because if we can't get that done, we don't really know how to manipulate the data. So what are the graph shapes we need to be able to recognize? Well, the one that we've already seen up to this point is going to be a nice, simple quadratic or parabolic relationship. So when I have A and B, what we have here is that A is proportional, remember this is a proportional symbol, to B squared, because B is on the horizontal axis. And if we wanted to make this a nice equal sign, what I would have to do to change it from proportional to equals is I would have to multiply one of these sides by a constant. So I would have to figure out, okay, what is this constant here, so I could figure out this graph, assuming that the y-intercept is pretty close to 0. So I'd have A is equal to some constant times B squared. Alright, so that's the first one. We can also see something like this. Now, this is basically a flip of the previous graph, and this is a square root. The square root is where it basically is going pretty quick initially, and then it tapers off, it flattens out. So this is the relationship where specifically C is proportional to the square root of D. Now, there's a couple of different ways you can do this one in particular. You could either say, to make it equals, that C is going to be equal to some constant times the square root of D, or sometimes we don't like to deal with square roots, so we could also do something like C squared is going to be equal to a constant times D. Now the next one, so it's going down and curving that way, and this is an inverse graph, where if I have E versus F, E is proportional to 1 over F. So therefore, to get an equal sign, I would say E is equal to some constant times 1 over F. And the last one we're going to want to be able to recognize is going to look very, very, very similar to an inverse graph. And this is an inverse squared graph. And the reason why we care about this is there's a couple of laws in physics that use this inverse squared relationship, where G is proportional to 1 over H squared rather than just 1 over H. And the thing is, you'll basically recognize, this is a pretty easy curve to identify, easy to identify. These look very similar, and it's going to be hard to distinguish between the two. So typically, if we are in a situation where we don't know which one to do, start with inverse. And if you linearize this for an inverse graph and it doesn't work out, then go to inverse squared. But more often than not, we'll probably be dealing with an inverse relationship. So let's go ahead and work through the linearization process and see how exactly we would go about doing it. So this is the exact same data we saw earlier when we have a person dropping a ball and we're seeing how much distance it has fallen through, and we get this nice clear curve here. So to linearize it, the first thing we need to do is we need to go ahead and figure out, okay, what is the type of relationship that we have here? And this is clearly, based on the graph shapes we just saw, a quadratic or parabolic relationship, meaning that D is not proportional to T, but instead explicitly D is proportional to T squared. So that is really crucial here. D is proportional to T squared. So here's the data once again, and now that we know that the relationship is D is proportional to T squared, I need to make sure I have a column of D, the distance, and a column of T squared, the time. So I need to essentially manipulate one of these variables. Well, D is perfectly fine. It's not going to change. But instead of T, now I need T squared. And keep in mind, when we manipulate this variable, we make it T squared rather than just T, I need to square my unit 2, so it is seconds squared. So what I'm going to do is just go down the line, and every value for T, I'm instead going to find T squared. So let's go ahead and do that. So I've got 0 squared is 0, 1 squared is 1, those don't change. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So now I'm going to plot this manipulated variable, which was T squared rather than T, against the unchanged variable, which was D. So essentially I've got my plot. I'm going to leave D on the same axis. So D was previously on the vertical axis. It's going to stay on the vertical axis. But on the horizontal axis, instead of T, I'm going to instead do T squared in the units of seconds squared. Now keep in mind, if you look at the previous graph, when it was T, this was 1, 2, 3, 4, 5. But now that I have squared them, this axis scale is going to change. So I'm going to have to change the scale a little bit. But now let's go ahead and plot the data points of D versus T squared. So for instance, this is 0, 0. This is 1 second, 5 meters. This is 4 seconds, 20 meters. This is 9 seconds, 45 meters, etc. And what we notice is this is most definitely a straight line now. We've basically made our curved graph now appear to be a linear graph simply by changing what exactly we are putting on both of our axes. Same overall data that we had originally, just now represented in a slightly different way. So now let's analyze it as though it was a regular linear plot. So if I just asked you to find the slope and y-intercept of this line, so to find the slope, we're going to pick 2 points. I picked 740 and 1160. So go ahead and find the slope. So 60 minus 40 over 11 minus 7, that gives me 20 over 4, or a slope of 5. So now, though, if I have this slope of 5, let's go ahead and write out our equation. So usually for a linear line, you write y equals mx plus b. But what do we have here? Well, first off, the slope is 5, and let's go ahead and give it the appropriate variable. So rise over run would be meters over second squared. So it's going to be 5 meters per second squared. That's my slope. My y-intercept is essentially 0 because in fact it is 0. So we don't need to worry about that. But remember, we have y and x here. If I write y equals 5x, well, that's not very useful. Instead, I need to put in the proper variables. Well, on our vertical axis, we have d, and on our horizontal axis, we have t squared. So this tells me the relationship between d and t squared is simply multiplying t squared by 5. And what that means is on the previous graph, the graph that was curved, if I want to know what the equation for that graph was, it is literally d is equal to 5t squared. We have found a more complicated nonlinear equation by essentially analyzing a linear graph. Now, we're going to utilize linearization many times throughout this year, and you're going to be able to get to the point where you can do it completely on your own. But let's go ahead and give another example so we can make sure we can do this fully and completely. So if, let's say, for instance, we've got two sets of data here. We've got y in meters, so we've got 0.25, 0.50, 0.75, etc. And we have the velocity in meters per second, 2.2, 3.2, 3.8, 4.5, etc. Now, if I'm going to go ahead and plot these against each other, I'll go ahead and tell you for this particular situation that we know y is the independent variable and v is the dependent variable, meaning that y should go on our horizontal axis and v should go on our vertical axis. And when we plot these, which I'll go ahead and do here, we get a relationship that looks like this. Now, it looks like it could be linear. You'll see there's definitely a curving at the beginning of the end, indicating that this is not actually a linear relationship. So let's go through those 5 steps once again and figure out what the exact relationship between these two variables is. So step 1, we need to identify what type of plot this is. Well, instead of having a happy face, we have a bit of a frowny face looking thing here, which indicates to us that this should be a square root plot. So v is proportional to the square root of y. The dependent variable is proportional to the square root of the independent variable. Okay, so we've got that. But now we need to manipulate one of our two columns to make this into a linear line. Now, this is usually where I see people make mistakes, because they look at this and they go, okay, do I square v? Do I square y? Do I square root y? Do I square root v? So this is what I want you to think about. One way to do it is simply look at the proportionality. If this is the proportionality, I want this variable and this variable. That's all there is to it. But let's say you were a little mixed up, you're a little unsure, and you want to double check that you've done it correctly. Well, if I want to make this into a straight line, well, what I need to do is I need v to increase at a greater rate so that the graph will bend upward, or I need to make y increase at a slower rate so that it more closely matches v's rate. So I need to get y to, once again, bend upward. So either I need to do something to make v bigger, or I need to do something to make y smaller. And since we know it's a square root relationship, I'm going to go ahead and say, well, if I want to make y smaller, okay, I'm probably going to need to take the square root of y. So let's go ahead and do that. So y I no longer care about. Instead, I'm going to do the square root of y, and therefore the unit is going to be the square root of meters. And I'm going to take all of these values, just plug them into my calculator, and figure out what the square roots of them are. So the square root of 0.25 is 0.5. The square root of 0.5 is 0.71. The square root of 0.75, 0.87, etc. And I'm going to leave v totally unchanged. So now we're going to plot these, and so to do that, I'm going to leave v on its same axis. It's still the dependent variable, and I'm going to put the square root of y on the horizontal axis, keeping in mind, if you look, I've changed the scales, so I'm going to plot these points with the square root of y and v. You can see this is much closer to a linear line. So I will now go ahead and draw a line of best fit and analyze this like it is any old regular linear equation. So I'm going to identify 2 points that are not data points on this graph, and I'm going to pick these two here. So I picked 0.4, 2 and 1.6, 7. And if I find the slope of these, I just do the change in y over, or the change in the vertical over the change in the horizontal. So 7 minus 2 over 1.6 minus 0.4. And if you plug that into your calculator, we get a slope of approximately 4.17. Now the units here are going to be a little gross. And in fact, a lot of times when we do linearized units, it's going to be a little gross, because this is going to be meters per second divided by the square root of meters. Now when we do this, ultimately what we have is the meters over seconds times the square root of meters. And what is meters divided by the square root of meters? That would be the square root of meters over seconds. So this is a bit of a more gross unit, but it is accurate. Okay, so I've done that. And now I could say, well, now I need to write this into a proper equation, and it's going to look like a linear equation, but by changing y and x, it will in fact no longer be linear. And so the slope was 4.17. The y-intercept is a little above 0, so I'm going to go ahead and include a y-intercept on this one. I'm going to change y, our vertical axis, to v, and my horizontal axis x to the square root of y, and we get an equation that looks like this, which is way more complicated than what we would expect to get from a linear graph. And in fact, this equation matches this yellow plot right here of this data relationship. So this curved relationship, I could say an equation for it is v is equal to 4.17, the square root of y plus 0.02. And then we are completely done. So what are our takeaways for this lesson on the data analysis technique known as linearization? Well, one, can we identify the relationship that two variables have with each other simply from the shape of their graph with respect to each other? So is it parabolic? Is it a curved smiley upward? Is it square root, a frowny face? Is it inverse, meaning that it is going to start high and then go low, or is it inverse squared, a more sharp version of that? Can we manipulate one of our data sets out of the two so that the relationship between them is now linear? And remember, to do that, we figure out the proportionality and just figure out, okay, I've got one part of the proportion, the other part proportion, those are the two I need to have. And then can we essentially analyze this like it is a perfectly linear plot? Pick 2 points, find the slope, find their y-intercept, and then write a nonlinear equation between these two variables simply from analyzing this linear plot.